Hello everyone. Today we're going to be talking about non-traditional machining. We sort of really already started this when we were talking about abrasive machining. We'll talk today about some chemical methods, electrochemical and thermal methods. Some of these are more common than others. Chemical machining, we're really talking about etching here. So a huge common application of this, printed circuit boards. Uh, so where you basically have some kind of a conductive layer like a copper layer, and you want to have some kind of a very intricate circuit pattern on it, and so you protect the area that you want to save of the copper, and then you chemically mill away the area that you don't want. And then you can put another insulating layer on top and keep stacking it up and get multi-layer circuit boards. Two's the most common, where you've got a layer on the top of it's usually a fiberglass wafer with a layer of copper on the top and bottom. Then the circuit, the part you don't want, gets etched away. 4 layers, two are common as well, where you do that. You make a 2-layer board, and then you put an insulating layer on either side, and then plate more copper on it, and then remove the copper you don't want. And you can stack that up to 40 layers or more in really high-end expensive boards. But two-layer and 4-layer are pretty common, especially for sort of DIY projects. Integrated circuits, too. The actual machining or the removal of material on the silicon wafers. Thinning parts for weight reduction, maybe cutting very thin, delicate parts that traditional machining wouldn't work on. So anyway, basically you've got your part that you want to mill or etch, or really it's etching is more common. So the part you want to etch, you put your mask on it. So the mask is what's going to protect material. You're then going to remove the mask somehow. There's lots of different ways of doing that. Then you're going to use some kind of a chemical compound to etch away the material you don't want. You're going to remove your mask, and you can repeat as necessary. Photochemical is very common nowadays, where instead of having to mechanically remove the mask, you've got a photoresist. You put a negative on the areas that you don't want, that you want to machine. You apply some kind of UV light or some other kind of light that cures the photoresist. So where it's not blocked, so where it's blocked, it doesn't cure, and the photoresist comes off, and the material can be machined or can be etched. Where it is not blocked here, the photoresist gets set by whatever kind of light, usually UV or something like it. Whatever the light is, it sets it, and where it's set, whenever you etch, that'll be the part that's preserved, that'll be the part that's removed. This is very common for printed circuit boards, is the photochemical method. Some defects you get on this, you'll get a little bit of overhang underneath the mask. It's just inevitable. You might get some islands. You might get the center being too thin, overworked here. So there's a lot of little tricks of the trade for getting this to work correctly. You can see that you can find some videos of people doing this for printed circuit board fabrication at home on the internet. I highly recommend not doing that for DIY boards. There's a lot of really good resources for having professionally made circuit boards. There's a U.S. company that will do small runs for $5 a square inch. There's some overseas companies that will do it for significantly cheaper than that for small runs or big runs. So there's lots of really good options for making circuit boards nowadays. And I've made a bunch of circuit boards for a mechanical engineer. And 2-layer boards, 4-layer boards, big power boards. I've done a lot of circuit board work, and it's so convenient just sending this stuff out and have someone make it. So yeah, this stuff you can do at home, but it's much better done by somebody that's knows all the tricks of the trade and has the correct equipment. Here's a little etched board like this, and again, this will be FR4 is the common material. I believe it's some kind of a fiberglass compound. Or phenolic, something like that. In the past they used phenolic, but this FR4 will be some kind of a fiber reinforced plastic in here. And then there'll be a copper layer, either something like 1 ounce or 2 ounce. And I don't know what it's 2 ounce, 1 ounce per something. I don't know what the denominator is on that. So 1 ounce per something copper. So you have to be a pretty big area, because 1 ounce of copper, it's a really thin layer. You're talking, just a few thousands. It's not that much of a thickness here. 2 ounces is pretty common. You get thicker than that, the cost starts to go way up. If you need to transmit a lot of power, these traces can get quite large. But for little traces like for an IC, something like that, these might only be 6/1000ths of an inch wide, something like that. For transmitting 30 or 40 amps of this thickness of copper, you might need a trace that's like a 1/2 inch to an inch wide, and might not be practical. You might use etching for very detailed work in metal like this, or this little hole array here, where drilling this out would take forever. Photo etching, you can actually do it quite quickly and fairly precisely too. Electrochemical machining, I'm not very familiar with. Essentially, you're reversing electroplating. So in electroplating, you're using an electrochemical process to apply a material to some kind of a substrate, apply a metal coating to some kind of a substrate. This is you're switching it around. So your tool is the cathode and your workpiece is the anode, which is backwards from when you're electroplating. And you still need it in some kind of a conductive salt and whatever the water is or the solution you're using. High flow rate, complete submersion, lots of the electrolyte moving through. Very high current density. Material removal rates very, very small here, right? 1/10 of a cubic inch per minute per 1,000 amps. You're just not removing very much here. So this would be a very specialized operation. So why is the voltage so low for this huge current density? Because you have a very, very conductive media, so you don't need a lot of volts to push that many amps. So you're relatively safe from a shocking perspective. Anything under than 40 volts or so, it's not that big of an electrical hazard, but there might have some thermal considerations here. So it's very specialized applications on this. I've not seen one of these. I've not been around one of these, and a lot of the examples coming up are aerospace applications. So it's mainly for doing weird operations in exotic materials is where you need to do electrochemical machining here. So complex shapes and hard alloys. Maybe if you need a surface that doesn't have any residual stress in it, polishing and deburring too. So very small holes, maybe 4/1000ths holes. Drilling, that's not really an option. So that makes sense to have some kind of exotic process when you need a lot of really small holes, like the cooling holes in turbine blades would be an example application for that. Depth to drill, 50-to-1 depth to diameter ratio. We're talking about gun drill range for very small holes. So that's a very attractive thing. These turbine blades, you're talking about really crazy alloys and really small holes, and traditional drilling is just not really a viable option for that. Again, the videos I'll link in the description. Electrochemical grinding is basically the same thing, but we're using a grinding wheel that machines in the same way instead of using an abrasive material. Here, again, pretty exotic material or exotic process here. So you wouldn't have the heat damage, burrs, and residual stress from abrasive grinding. Your wheel's not going to wear as much. For very fragile parts like honeycomb, things like that. I don't know why you'd machine a honeycomb, but maybe you need to. Surgical needles, really fine machining, tips of a turbine blades, grinding very hard materials. Be applications for that. EDM is fairly common. Electrical discharge machining. So essentially you are sending an arc from your tool to the workpiece, and the arc causes material to, wherever the arc lands, it causes material to erode away and explode out basically. So you're producing lots, thousands of sparks per second. It melts and vaporizes the material you want to remove. This is used for tool and die making a lot, for machining really hard tool steels that at their full hardness that would be very difficult to traditionally machine. You really need some kind of abrasive process for a lot of this. And EDM is very precise, and it's capable of machining very hard materials. So you get really good, but it's a very characteristic surface finish. It's a matte surface finish, since you're basically machining by making little pits. It doesn't leave a very nice, it's a very smooth but matte looking surface finish. Your accuracy can be amazing on EDM. 1/10 of a thousandth is pretty easily doable with EDM. I mean, parts that, and you have I've seen some widgets that people have made on EDM machines that be like a spline going into a socket for the spline that are a vacuum seal, so that I mean, honestly, you don't even need a seal between it to hold air pressure. Uh, so I mean, even air can't leak past. I mean, just an incredibly good surface finish. It's fairly slow, fairly expensive, but it does some pretty nice, amazing things. You need a dielectric, some insulation between the tool and the workpiece, so you get sparks. If you didn't have that, if they basically touched each other, you'd just get a short circuit, and you wouldn't get sparks. It would erode the material. So you need some kind of a dielectric in between the tool and the workpiece to guarantee the voltage gets high enough that you actually get the sparks that cause erosion. And then, yeah, you need something when it breaks down to carry the spark. So you need a very specific dielectric. And it's going to be a coolant and a flushing agent. And I think a lot of these actually are water-based. But I've not run one of these, so I can't say for experience. But you just basically need some kind of a dielectric. You couldn't just do this out in the air, because then that'd be bad. You get all sorts of oxidation. And you don't want something that's too conductive here. Otherwise, you don't get sparks. You just get current conducted through it. So you need high voltage to cause the breakdown. So you're going to use a pulse generator to do this, and you're going to need thousands to tens of thousands of volts probably, and depending on the dielectric, to break down and cause the sparks to happen. This is plunge EDM, where you've got a tool that's the negative of what you want to machine, and you plunge it in and very slowly plunge it in and remove material to the shape of the tool. So this would be something like an application I've seen is making very, very fine features in a mold, in a very hard tool steel die, machining something very intricate like letters or something like that, or like a company logo, something like that, machining it into a hardened tool steel die. Wire EDM's common too. Here, it's the same basic process, but I use a continuously threaded or continuously moving wire, and it's essentially basically the current arcs from the wire to the part, machines an area around the wire, plus a little spark gap here, so that the actual cut width is a little wider than the wire diameter. And you can use it basically like a cheese cutter to cut very, very hard metals that might be very, very difficult to machine. And you can cut very sharp corners, things like these rotor slots and or a stator slots. This would be a rotor slot in like an electric motor, but you can cut stator slots too. Sharp corners, fine, all sorts of different applications where, spline and things like that, making custom internal gears. Wire EDM is fantastic for it. It's a fairly expensive process. You got a lot of consumable here in your wire. You need the dielectric. It's fairly slow. It's a fairly sophisticated machine, but there's really no other process that can do what it can do. You can get ones that the top and bottom heads will move independently. You can get tapers and things like that. But it's a really, really great process and really, really amazing surface. Not surface finish. Surface finish is matte. Really amazing accuracy, dimensional accuracy. So all sorts of widgets here. We've got a lot of these are rotors for electric motors, for prototyping electric motors, and here the rotor and stator, and really, really hard to machine materials. And something like this, machining this with any traditional methods would be a nightmare if it's even possible. For mass production, this isn't going to work, though. It's a slow, expensive process per part. But for making prototypes, it'd be fantastic. And again, the videos I'll link. Electron beam machining, fairly small features. I'm not experienced with that at all. Laser machining is actually fairly common. Now, I'd almost move it out of non-traditional. It's become common enough in sheet metal fabrication. Plasma arc cutting too is again, that's not really non-traditional in 2020. It's been around a while and pretty common. So laser machining, this is some kind of like a CO2 laser or something. And you see CO2 lasers. You're seeing a lot more diode lasers and other kind of fancier lasers that will hopefully drive the cost of this down. The lasers, especially when you start getting into multi-kilowatt industrial lasers, they get very expensive very, very fast. You might have some kind of a just a lens and mirror setup for getting the laser around. You might have a fiber laser that's in the more expensive machines. You'll see a fiber optic carry the laser. But essentially you're sending a lot of photons out in a straight line, and they're impinging on the surface and vaporizing and removing material. So a lot of very high energy photons being generated, and that's what you're cutting with. You probably have some kind of a jet of a gas, either reactive or non-reactive, depending on what you're doing, to sort of help blast the material away and clear it away so the laser can cut new material. CNC machine almost always. I've seen there's some crazy hand laser stuff on YouTube. Someone's got some hand laser cutter for decommissioning like nuclear power plants and other things where you really need to get in there quick and cut stuff up. And it's a laser cutter that's handheld. It's pretty cool. Pretty freaking dangerous. But anyway, you see a lot of these in sheet metal processing, and pretty small size sheet metal operations might be able to justify the cost of a CNC laser cutter because they're just so flexible. Fast too. Man, they're fast. Different lasing materials here, different wavelengths. Different wavelengths work on different materials. CO2 is pretty common on the cheaper ones, the hobby ones that are somewhere around the tens of kilowatts. No, not tens of kilowatts. Tens of watts. Tens of kilowatts would be a big laser. So something like a 20, 30, 40, 50, up to 90 watt laser, something like that. A lot of those are CO2 lasers. High power density needed for cutting here. Fairly short interaction time with the material here. And you can do a lot of different things. You can do surface hardening with a laser for heat treatable materials. You can glaze and micro machining and doing all sorts of other fun things where small interaction time but high power density. So power range here, 5 milliwatts you're not going to do very much with when it comes to machining. For metal cutting, you really need a kilowatt and up laser. 5 kilowatts a number I've heard thrown around a lot for industrial lasers, and they start to get pretty expensive. Your megawatt lasers here, that's like a military laser. That's a serious laser, and maybe in some industrial applications, but that would mainly be for a short duration of time, so it'd be pulsed high power. A continuous 1 megawatt laser. I don't even know if that exists. Maybe it does. That's a serious laser. That's like a sci-fi spaceship killing laser thing, is a continuous megawatt laser. So maybe that exists. I'm not sure, but I know the military, one of their applications for shooting missiles down with lasers, they took about 6 5 kilowatt industrial metal cutting lasers and sort of ganged them together to make a 30 kilowatt laser and made a turret out of that, and they were testing it on a ship. So they give you some idea. 30 kilowatts or so is a pretty serious military laser. A megawatt would be 30 some times that. That's a very serious laser. Again, I'll link the videos. Plasma arc cutting, fairly common. So lasers are expensive. Plasma's pretty cheap. A good plasma cutter's a few $1,000. A good CNC gantry's a few $1,000, up to $5,000 to $10,000. Put them together, for $15,000 to $20,000, you can have a CNC plasma cutter. So even a small shop can afford that. It's on the same level as a nice mill or lathe. You can get a nice plasma cutter. And you can get cheap knockoff ones that are even cheaper too. So you basically it's a TIG welder that the power's turned up more on. So and you've got actually it's kind of like a combination of a MIG and a TIG welder where you're not actually depositing material. You've got a tungsten electrode. You create an arc. The arc is hot. It creates a $30,000 to $60,000 Fahrenheit or so ionized gas. So it causes your primary gas to become a plasma and be very, very hot and very, very conductive. And you get an arc from the electrode down to your base material here. That superheats the gas. It'll be pressurized, and you get a hot pressurized gas shot through a nozzle here, and that's going to vaporize whatever material you're trying to machine. And then you'll have your primary gas. The jet will also help clear the material away too. So you really need a primary gas flow on this. Some applications, on smaller, cheaper applications, it'll be air. You might use something more sophisticated than that, but air is pretty common. You might have a shield gas, not always. A lot of the machines I've seen don't the hand hobby ones, they don't have any kind of a shield gas. Continuously running argon or something like that, which you really would probably need argon in this. It'd get expensive. Argon's fairly cheap in the grand scheme of things, but still, it's not something you'd want to be running on a hand plasma cutter unless you were doing something that really needed to not be oxidized. Fairly fast, fairly aggressive cutting, fairly poor surface finish on this. And you might get slag on steel. You can get slag, it's pretty common. Pretty big heat affected zone, pretty big taper on this too. So, for thin stuff, it's hard to get precision on it. I've done quite a bit of plasma cutting, CNC plasma cutting. Thin stuff, it's sort of hard to get precision. When you're somewhere in the, I don't know, 1/4 inch range, it's a pretty attractive process, up to 1/2 inch. And you start getting a pretty big kerf at a 1/2 inch. Anything past that, it starts to be, if you can still do it, but once you get up to like inch plates, you might get into CNC oxyacetylene at that point. Plasma still works up to that, but you're starting to talk about a pretty serious plasma cutter. But 1/2 inch down to about 16 gauge, it works pretty well. Thinner than that, you start to get into issues depending on what the plasma cutter is, as far as just not cutting very good holes, not very clean holes. And again, I'll link the videos. So that's it for today. Thank you all.